Hi guys, welcome back to Nunley Math. I'm Aaron Nunley. Thanks for joining me here today for our discussion of the vertex form of functions. The vertex form of functions. Now in my classroom, we are well into our functions unit. We've already talked about domains and ranges and how our function is the map that connects those two things to one another. We've also talked about 7 major function families as well as what the graphs of each family of functions might look like. And then we've talked about some shortcuts that we can use in order to graph those functions. Now, in the last lesson or two in my class, we would have done an investigation using an online graphing calculator program called Desmos, D-E-S-M-O-S, that allows us to put functions in, and it creates the graph for us. And we would have typed in a root or basic form of each of our function families, and we would have investigated how different changes in the function would make changes in the graph of that function. So what I'm going to do here, since you guys were not able to be a part of that, is I'm going to go ahead and show you the vertex forms for each of our different types of functions. Notice that we have our linear function, our absolute value function. It can be identified by those absolute value bars. Our quadratic function that has x raised to the second power. Our cubic function that has our x raised to the third power. Our exponential function where you have x in the exponent, our square root function where you have the x under a square root sign, and a rational function where the x is in the denominator of the function. Now, if you are uncomfortable with the 7 different function families that I've just identified for you, then you are watching the wrong video. You're going to want to go back and look for Aaron Nunley and type in the different function names, and certainly you can pull up the YouTube video for each of those and learn about them individually before you begin this lesson. The reason I put these all here together is I want you to notice that each of these functions has a letter A in it. Each of these functions has the letter H in it, and each of these functions has the letter K in it. Each of these letters in each of these functions always do the exact same thing, and that was really the point of the investigation we had in class. So for example, in each of these functions, no matter what the basic function type or shape is going to be, A always controls the steepness of our graph. For example, if I make A into a very large value, then the graph is going to get steeper. And if I make A into a very small value, the graph is going to get less steep. And then we learned that negative values of A will flip that graph upside down. That's going to help us when we're trying to graph our functions quickly, as you'll see in the next couple slides. In every type of function, no matter which type I pick, the letter H always does the same thing to my function, and that is it moves the graph right and left. If H is a positive value, the graph is going to move to the right. And if H is a negative value, the graph is going to move to the left. A lot of people find this confusing because you'll notice that we have a minus sign here. So when we do x minus a positive number, then the graph is going to move to the right. X minus a negative number, the graph is going to move to the left. Sometimes we get plus signs in here, and people find that to be rather difficult to conceptualize. So what I tell people to look for is what makes this value inside the parentheses or absolute value bar, or under the square root sign, or in the denominator. What makes that value into a 0? We'll talk about that here in just a moment. And in all cases, if we add a number to the end of our function, this plus k on the end, that's going to move my graph up and down. If k is positive, the graph moves up, and if k is negative, the graph will move down. So what we're going to do is we're going to do several examples of functions that are written in vertex form. Notice that I've put the things we just discussed over here on the left so that we can refer to them, and then I've created a table and given you a coordinate plane. I'm going to talk you through the process that I use when I'm graphing these types of functions. Hopefully you'll find this, this pattern seeking to be a lot easier than just plugging in values one at a time and trying to guess what our graph is going to look like. Whenever I start working with a function, I always begin by looking right here and I say, what kind of a function is this? And I happen to notice that I have an x to the first power. There are no absolute value bars or square root signs or exponents to do anything weird to it. So I can tell you before I ever begin working on this problem that I'm going to be dealing with a linear function. And that's important because if I know this is a linear function, then I know that my graph is going to make a straight line. It might slant up, it might slant down, the steepness can vary, but every time it's going to be a straight line. If I know that before I start, it takes a lot fewer values in my table in order to get the graph. The third thing I always think about is what is the domain of my function? You'll remember the domain is where this graph goes from right to left. And if I look at my line over here, you'll notice that it's going to go to the right forever. It's going to go to the left forever, making my domain all real numbers. Now I did use our fancy function notation right here. This says all x's work as long as or such that that x is a real number. In other words, any number that can be found on a number line can be plugged into this function. So the other thing that I know is that my range where this graph goes up and down is also all real numbers. Notice the f of x will work as long as that f of x is a real number or can be found on a number line. Notice from the graph it goes up forever and it goes down forever. All of this ought to be reviewed and should be pretty comfortable to students in my class at this point. It is not the focus of what we're trying to do here today. So here's what I want us to focus on that might be new. If I look just at what's in this set of parentheses, notice I have an x minus 3. This 3 occupies the h position. The h position in the vertex form of my linear function. Remember, it's always x minus h. And this one happens to be a 3. So I'm going to go ahead and put that into my table. I'm then going to look over here and see what was added to the end of my function. Notice it's a plus 5. Now, I can go ahead and plug in my 5 because I know that if I plug in a 3, 3 minus 3 is 0, 2 times 0 is 0, plus 5. It's going to be a 5. But that's not what's most important. What's most important for me is to realize that 3, 5 is going to be a point on this graph. We're going to find throughout all these examples that when you look at h and you look at k, those are going to change how your graph is moved. Ordinarily, if I'm graphing a linear equation, and actually if I graph any equation, ordinarily I'm going to start at 0, 0. But because I have this minus 3, I'm going to go to the right 3 places. 1, 2, 3. Because I have this plus 5, I'm going to go up 5 places. That's what the h and the k tell me. It says, don't start at 0, 0, start at 3, 5. But that's not all. When I look over here at the a, remember the a tells me that the steepness is going to change. Since this is a 2, I'm going to have a linear equation that grows twice as fast as what I would normally expect. Linear equations in their most basic form go in a straight line, up 1 over 1, up 1 over 1, up 1 over 1, up 1 over 1. But because there's a 2 here, I'm not going to go up 1 over 1, I'm going to go up 2 over 1. I'm going to grow twice as fast as normal. Let's do that again. Up 2 over 1, up 2 over 1. You could even do down 2 and backwards 1 because negative 2 divided by negative 1 is a 2 as well, and so on and so forth. Notice you can use that to get your straight line. This is the graph of this function, but more importantly, I want you to realize that I was able to graph this linear function with only finding 1 point. Ordinarily, you'd have to find 2, 3, 4 points. But by recognizing that the graph was going to move 3 places right, 5 places up, and grow twice as fast, I was able to get the graph very quickly. Mind-blowing, right? Let's try another one. This is function g of x. G of x equals -3 times the absolute value of x plus 4, absolute value, plus 9. I'm going to do the same things I did on the last graph, and we're going to see what this is going to look like. Remember, you always start by trying to identify the type. Can you do that? Hopefully these absolute value bars were a pretty good clue that this was going to be an absolute value function. And hopefully you realize that absolute value functions always make the same shape. They always make that V. Once I know the shape that it makes, I want to begin thinking about the domain. Remember, the domain is where this graph goes to the right and where this graph goes to the left. Notice it's going to the left forever, it's going to the right forever, which means my domain is every x will work as long as that x is a real number, meaning as long as that's an x that can be found on the number line. What about the range? Where does my graph go up and down? Well, hopefully you can see it's going to go up forever, up forever. Notice it's coming down to this point, and then it's going to go back up. As long as my values are greater than this point, I know that my range is, or that my value is going to work. In other words, I can stick any x in I want, but whatever I get out will always be bigger than this point. Ordinarily, this would say all g of x as long as g of x is bigger than this point, but notice I've made it a less than or equal to that point. Do you know why I used less than? Take a look back up here at my function. Notice the a in this function. A controls the steepness of my graph. And since it's a -3, I know that my graph is going to be upside down. In other words, when I go to graph this, instead of getting my V to look like that, it's going to look like this. I'm always going to be less than this point or equal to this point. Little tricky, right? Ordinarily, it's greater than, but because I have a negative a, I know it's going to flip over and be a less than. Let's look at h and k real quick. X minus 4 is in the absolute value bars. Notice that this would be x minus -4, but I prefer to think of it as what would make this value into a 0. Well, that's -4. In this case, my h is going to be a -4. Notice over here for k, I have a 9. If I were to stick a -4 in, -4 plus 4 is going to give me a 0. 3 times the absolute value of 0 is 0, plus 9. The point -49 is going to be on my graph. But it gets even better than that. Because ordinarily, I would start off at 0, 0. But when I look at my h and my k, I know that my graph is going to start off at -4, 9. In other words, instead of having a vertex of 0, 0, this point right here is my vertex. And if it's my vertex, that means my line of symmetry is going to pass through that point. Now, up until now, when we were graphing absolute value functions, let me clear all this off. When we were graphing absolute value functions, we had to keep sticking in numbers and sticking in values and guessing and checking until we found the vertex. But since this is in vertex form, we can find the vertex right away. Oh, that's why we call it vertex form. Interesting. And guess what? Because my a is -3, I know that from this point I'm going to come down, and that there's going to be a line of symmetry between those two spots. And I also know it's going to go down 3 times as fast as what it would normally do. In other words, instead of coming down 1 over 1, it's going to come down 3 over 1. By the way, that also gives us the range, doesn't it? I'm always going to be smaller than 9. Okay, there's my down 3 over 1, and I get its reflection. Down 3 over 1 again, there's its reflection. And I can continue that down 3 over 1 as long as it takes for me to figure out what my graph is going to look like. What do you think? That's not too bad, right? Because 3 is such a large number, my graph is skinnier and steeper than it would normally be. Because it's a -3, it's also upside down. Notice I was able to graph this with just 1 point in my table. And in reality, if I wasn't doing this for you for the first time, I probably wouldn't have even bothered to put that in the table. Pretty cool, right? Gonna try another one? Let's do another one. Can you figure out what type of function this is? If I look right here, notice I see a square that applies to the x. That's going to make this a quadratic. It also means that my shape is going to be a parabola. Now in this case, notice that your parabola is going to have an a of 1/2. That means it's going to grow half as quickly as you would normally expect, so we can anticipate having a wide parabola. Notice as well that it's positive. That means that this one is going to be right side up. It will not be upside down. What about the domain? We found the name, we found the shape. What's the domain? Well, let's see, the graph goes to the right forever, it goes to the left forever. Your domain is all real numbers. What about your range? Well, let's see. It's going to go up forever, come down to the vertex, go up the other way. That means it's always going to be bigger than this vertex. Always going to be bigger than the vertex. It could be equal to the vertex, but we're never going to go below that vertex. All h of x will work as long as h of x is greater than or equal to that vertex. Let's find where that vertex is. Coming back up here, I'm going to ask myself, what is going to make this into a 0? Hopefully you realized it was a -6. And then I'm going to come over here and look at this k of -10. Remember, if I stick a -6 in here, it's -6 plus 6 is 0. 0 squared is 0. Half of 0 is 0. Minus 10 gives me the -10. That tells me that the vertex of this parabola, or of this quadratic function, is going to be at -6, -10. That means my line of symmetry will also go through that point. Now, if this was just me doing this, I would actually go ahead and use a pattern that I happen to know for quadratics, and I could finish graphing this without ever plotting any other points in my table. But in my class, we haven't talked about that pattern yet, so I'm not going to assume you know it here. Make sure you check out our quadratic functions video to pick up that pattern. Since my vertex is at -6, I'm just going to stick in numbers that are close to that vertex because I know this graph is going to start growing, and if I get too far over here, I'm going to end up with numbers that are off my coordinate plane. By the way, we know we're going to be greater than that -10 because that is our lowest point. If I stick in a -5, -5 plus 6 is 1, 1 squared is 1, half of 1 is a half, minus 10 is -9.5. And then I get the reflection of that. Now, I'm not going to go through and do all of the computation for you. If you would like to see that computation, I would recommend that you pause the video and try it, especially if you're a student in my class, because you're going to have to do this without a calculator on your test. But because our focus today is on the graph of the function, I am going to do this just a little bit faster. Remember, pause the video as you need to. And remember that every time I get a point, I also get the reflection until I can see the graph. Notice it grew by a half, then it grew by 1.5, 2.5. Let's see, what is this? 3, 4.5, and then it grows by 1, 2, 3, 5.5. There is a pattern that exists in here. If you can pick that out, that's going to make this a little faster for you. If not, don't worry, we'll cover it in a later video. Not too bad, right? Now, this one did require us to use more points in our table, but this is definitely less than we would have had if we just started plugging in 0, 1, 2, 3 like normal. If we'd started with those values, we would have gotten things that are way up here off the graph, and that would have been very, very frustrating. Here's another one. Do you know what type of function this is? Pause the video if you need a minute to think about it. Notice that my x is in my exponent. That makes this exponential. Exponential functions always have the same shape. They're always going to look like this. Now remember, they are approaching an asymptote right here, but they will never reach it. If I look at where this goes to the right and to the left, you should see that it goes on forever in both directions, so your domain is all x as long as x is a real number. If you're looking for where this goes up and down, you can see that it goes up forever, but when it comes down forever, getting closer and closer to the asymptote, but never quite reaching it. That means my range is that I'm always going to be greater than the asymptote. All j of x will work as long as j of x is greater than this asymptote. We don't know where that asymptote is, but we're going to find out pretty quickly. When I come over here, you will notice I have an x minus 4, or I should say an x plus 4. I'm going to ask myself what's going to make that into a 0, and of course that is a negative 4. That's my h. I'm going to come over here and I'm going to find my k. It's a negative 5. Notice this time that if we plug a negative 4 into my function, negative 4 plus 4 is 0. 2 to the 0 is 1. 1 minus 5 gives me a negative 4. So I am going to start off with that point negative 4, but I want to talk about this negative 5 for just a second. Because in an exponential function, that negative 5 gives me my asymptote. Kind of cool, right? Now, if we had spent more time working with these, I would have told you that you could actually look at your a value, this 2 right here, and the a value would allow you to do the rest of this graph without putting points in the table. You, however, probably don't know that pattern yet, so what we're going to do is we're going to pick points that are close to this one, and we're going to begin working our way up until we can see the pattern. So this is negative 4. I'm going to plug in, let's see, I'm going to plug in a negative 3. Oh, the domain. Or the range, sorry. The range value, you'll notice, is negative 5, greater than negative 5 because we're always approaching that asymptote, but we're never going to reach it. Notice that it's a little out of place. I'm going to need to move that after I finish this recording. So we're going to pick some values that are close to negative 4. Let's go with negative 3. Negative 3 plus 4 is 1. 2 to the first is 2. Minus 5 makes negative 3. I'm going to plug in a negative 2. Negative 2 plus 4 is 2. 2 squared is 4. Minus 5 is negative 1. And I'm going to continue doing that until I run out of space on my graph. Notice I can now see that I'm curving right up here, but I need to figure out what to do to the left. I'm going to stick in a negative 5. That gives me negative 4.5. Negative 6 gives me negative 4.75. And there's our graph. Looks just like this. Now, notice from this first point right here, if you look at how you're growing, you went up 1, 2, 4, 1, 2, 3, 4, 5, 6, 7, 8. You grew 1, 2, 4, 8. That's a very interesting pattern. It is one that's predictable. If I go back the other direction, I go down a half, then I go down a fourth. Very interesting. As you begin to notice those patterns, you're going to have to do less and less work over here in the table. Let's take a look at k of x. K of x equals 4 divided by x plus 3 minus 5. Any idea what kind of function that is? Well, hopefully you realize that is a rational function. And if you know it's a rational function, hopefully you remember that it makes a shape that's very distinctive. It's got those two curves that are separated by a vertical asymptote and a horizontal asymptote. The real question for us when finding our domain is, where is that asymptote? Because I can go forever to the right, I can go forever to the left. The only space right and left I can't go is where that vertical asymptote is. Do you remember how to tell where that vertical asymptote is? In my class, we discussed the fact that when you have a fraction, you're never allowed to divide by a 0. So that asymptote is going to be whatever x makes this into a 0. Any idea what that is? Well, hopefully you know that's a negative 3. Because if you were to plug in a negative 3 plus 3 is 0. 4 divided by 0 is undefined. So we can put in a vertical asymptote right there. Let's think about the range. I can go forever up. I can go forever down. The only place I'm not allowed to go is wherever this horizontal asymptote is. So when I go to give my range, it's going to be all k of x as long as k of x is not whatever this line is. So we need a way for figuring that out. Let's come back over here to our table. If I see this minus 5 right here, this is my k. This k will always tell you where that horizontal asymptote is. And you can draw it. You see, down here, this x plus 3, the h, can I draw an h? The h gives you the location of the vertical asymptote. The k gives you the location of the horizontal asymptote. And now we already, without plotting any points at all, have a pretty good idea what our graph is going to look like. It's going to come around here like this somehow. And it's going to come around here somehow. And we're going to be done. So what I'm going to do is I'm going to delete those, erase that ink, and I'm just going to start plugging in some points to see if we can get a better picture before we do our sketch. Since my asymptote is at -3, I want to pick things that are close to -3, so I'm going to stick in a -2. -2 plus 3 is 1, 4 divided by 1 is 4, minus 5 is -1, and there's your dot. I'm going to do the same thing with -1 and get a -3. I'm going to do the same thing with a 0. That's going to give me 4/3 minus 5, which is -3 2/3. If I put in a 1, I get 4 divided by 4, which is 1 minus 5 is -4. And I'm going to continue doing that until I get enough points to see where my curve is headed. Sometimes people get a little antsy about what's going on up here, so I'm going to go ahead and stick in a -2.5 as well. That's kind of in here, and that gives me a 3. Once I have those dots, I know where my curve is. Please ignore this little, I don't know what you call that, little twist right there. That was an accident. I'm not quite sure how that got in there, but certainly it doesn't belong. That should be a nice smooth curve. It was a little glitch. I tried it twice and couldn't get it to go away, so we'll just make a mention of it. Once we know where this is, we know the graph down here. The other side is going to be a 180-degree rotation around this point, which means since this is over 2 and up 2 to get to this point, I'm going to go backwards 2 down 2 to get my other point. Notice that this was forward 1, up 4. I'm going to go backwards 1 and down 4 to get this point. And I'm going to go forward 4, up 1, so down 1, backwards 4 to get this point. Notice that it's beginning to make the exact same shape. You can put in as many points as you need to in order to be comfortable, but that's sufficient for me today. I think you get the idea. And there's your graph. Notice this one got the little where's my cursive? There, the little bend in it as well. That's a computer glitch. I don't know how to get rid of that. How about this one? M of x equals -square-root of x plus 2 plus 6. I think you have the idea now. We're going to start with a type of function. It's a square root function. Square root functions always make the same shape. It's going to look like this. Notice this one has a -1 in front of it. -1 means that this one is going to flip upside down, which means it's going to look kind of like that. When I go to do my domain, since it's going to go to the right forever, all x will work as long as x is bigger than this point right here. It could also equal that point, but we will never be smaller than that point. Do you know where that point is? Hopefully you remember in my class that we said there's a rule for square roots that will help us determine where that point is. And the rule is you can't square root a negative, which means whatever makes this into a 0 is the smallest value I'm going to be able to use. Do you know what that value is? Well, of course, it's a -2. When we talk about the range is wherever it goes up and down. It's going to start at this point and go up forever, except for the fact that ours is flipped upside down, which means it's going to start at this point and go down forever. So your range will be all m of x as long as m of x is less than or equal to wherever this point is. Fortunately for us, that's what the +6 tells us. That's your k. Your k says start off down here at +6. What that means is we can start off by graphing the point -2, +6. That's the vertex of our graph. And we can begin to plug in values for x, solve for m of x, and plot our points. If I stick in a -1, -1 plus 2 is 1, square root of 1 is 1, -1 is -1 plus 6 is 5. If I were to stick in the next value, which would be 0, I'd get a 0 plus 2, but I don't feel like doing the square root of 2, so I'm not going to do that. If I were to plug in a 1, 1 plus 2 is 3, the square root of 3, yeah, that's an irrational number. I don't want to do that. If I were to plug in a 2, though, 2 plus 2 is 4. The square root of 4 is 2. -2 plus 6 makes 4. Again, for those of you that are not in my class, you'll notice that a lot of my students are not filling in this center column. This is a workspace for you. If you would like to show your work, you are certainly welcome to do that. But I've told my students if they're comfortable and confident and feel like doing that in their head, they're welcome to do that. They're just responsible for the consequences if they begin making calculation errors. And again, I'm going to start picking numbers that work that do not give me irrational numbers. I picked a 2. If I put in a 3, I get a 5, 4, 5. I want to pick 7 because 7 plus 2 is 9, and 9 is a perfect square. I get 7, 3. The next perfect square is going to be 14 plus 2, which is 16. The square root of 16 is 4. -4 plus 6 is 2. And that's going to be off my space. I can go ahead and connect that, and that's what your graph looks like. Hopefully this has been useful for you. Again, as you get better and better at looking at the form of your function, finding those h's, finding those k's, and looking at your a's, this should become easier and easier for you. For me, that's all I've got for you today. Hopefully this has been useful for you. If it has, make sure you give us a big old thumbs up. Make sure you ring that bell to turn on your notifications so you can hear everything new coming from us here at None of the Math. As always, I do wish you all the very best. Take care of yourselves. Bye-bye.